Principles of remote sensing. Electromagnetic energy and spectral signatures. Remote sensing is the science and art of acquiring and analyzing information about objects or phenomena from a distance. As humans, we are intimately familiar with remote sensing in that we rely on visual perception to provide us with much of the information about our surroundings. As sensors, however, our eyes are greatly limited by 1. Sensitivity to only the visible range of electromagnetic energy. 2. Viewing perspectives dictated by the location of our bodies. And 3. The inability to form a lasting record of what we view. Because of these limitations, humans have continuously sought to develop technology that would enable us to increase our ability to see and record the physical properties of our environment. Why remote sensing? The Society of American Foresters, the national scientific and educational organization of the forestry profession, compiled a top 10 list of forestry-related advances in the United States over the past century. One of those advances was remote sensing and other technologies. Through technology such as remote sensing, foresters can monitor the health of the forest, target management activities, map fire outbreak, and identify wildlife and fish habitat for protection. Why remote sensing? Satellite remote sensing, with its synoptic view of the Earth's features, regular repetitive coverage over large areas, and digital mode of data capture, offers an effective means of inventorying and updating natural resources information, monitoring land use changes and environmental impacts near real time, and providing a historical profile for the purpose of policy formulation. Why remote sensing? Together with Geographic Information Systems (GIS) and Global Positioning Systems (GPS), remotely sensed data can be analyzed spatially, rapidly and accurately for timely decision-making in order to address current issues relating to natural resources security, natural disaster mitigation and environmental protection. Malaysian Center for Remote Sensing (MACRES). Why remote sensing? Different rock types, vegetation, snow depth, topography. How to remotely sense. Passive sensors. Object equals target I equals sensor. Following are design. Passive sensors. Beyond vision. To remotely sense. Active sensors. Following are design. Active sensors. Radar. Lidar. To remotely sense. A. Source of EMR. B. Electromagnetic radiation, EMR. C. Object of interest. D. Sensor. E. Transmission to receivers. F. Data products. G. Results of analyses. Formally, a remote sensing system. A. B. Lambda. F or V. Note that different groups reverse the order, placing gamma rays at the far left. The glue that holds it all together. Electromagnetic radiation. Wavelengths lambda are the predominant means by which we, geographic remote sensors, refer to EMR. Wavelengths are inversely related to frequency f by this equation. C equals lambda f, where c equals speed of light, a constant. Thus, as the lambda increases, the f decreases because c is a constant. Frequency is directly related to our ability to detect the wavelength. Since the lower the f, the less the energy, i.e., photons. Waves, particles. Also, think about the relation between temperature and wavelength. F equals V. As a result, the longer the wavelength, the harder it will be to detect. This means that the detector needs to be more sensitive in order to detect it, and/or the source area needs to be larger in order for the sensor to capture enough energy from the target area. This is why, in most remotely sensed data, less spatial detail is available for passive infrared images. Waves and photons. Sensor. Blue. Green. Red. Sensor. Near. Infrared. Near. Infrared. Sensor. Far. Infrared. The visible spectrum. Wavelength. M. 1 meter equals 109 nanometers m. Why we see the colors we do. The visible spectrum. The sun emits electromagnetic radiation at many wavelengths across the M spectrum. These images show the sun in the infrared, visible light, 4 different ultraviolet wavelengths, and in X-rays. Images taken in very narrow bands have the wavelengths of the associated waves noted in nanometers. The photosphere is most prominent in the visible light images, while UV and X-ray views show details of the solar atmosphere. Note that almost all of these images are false color representations, since your eyes cannot see X-rays or ultraviolet or infrared light. The source for most systems. The wavelength of maximum emission of any body is inversely proportional to its absolute K temperature. Thus, the higher the temperature, the shorter the wavelength that is emitted the most. This phenomenon is often called Wien's law. The following equation describes this law, where B is a constant approximately 2,900 μmK. T is the temperature Kelvin, where the amount of electromagnetic radiation emitted by a body is directly related to its temperature. If the body is a perfect emitter, i.e., a black body, the amount of radiation given off is proportional to the fourth power of its temperature, as measured in Kelvin. This natural phenomenon is described by the Stefan-Boltzmann law. The following simple equation describes this law. How much? The area under the curve. Stefan-Boltzmann law. 1 meter equals 106 micrometers. Stefan-Boltzmann and Wien's laws. Note how the infrared wavelengths are divided into near IR and far IR. The sun's temperature is around 6,000 K. The Earth's temperature is around 300 K. Note that the graph axes are logarithmic. Wien's and Stefan-Boltzmann laws. Demo. What happens to EMR in the atmosphere? Passive systems. Beyond vision. To remotely sense. In remote sensing of the Earth, the sensor is looking through a layer of atmosphere separating the sensor from the Earth's surface being observed. Hence, it is essential to understand the effects of atmosphere on the electromagnetic radiation traveling from the Earth to the sensor through the atmosphere. The atmospheric constituents cause wavelength-dependent absorption and scattering of radiation. These effects degrade the quality of images, although some of the atmospheric effects can be corrected for. The atmosphere. Rayleigh scattering occurs when particles are very small compared to the wavelength of the radiation. These could be particles such as small specks of dust or nitrogen and oxygen molecules. Rayleigh scattering causes shorter wavelengths of energy to be scattered much more than longer wavelengths. Rayleigh scattering is the dominant scattering mechanism in the upper atmosphere. Why the sky is blue? 1. Sun's angle. Why sunsets are red? Mie scattering occurs when the particles are just about the same size as the wavelength of the radiation. Dust, pollen, smoke and water vapor are common causes of Mie scattering, which tends to affect wavelengths longer than those affected by Rayleigh scattering. Mie scattering occurs mostly in the lower portions of the atmosphere where larger particles are more abundant, and dominates when cloud conditions are overcast. Why clouds are white? Absorption is the other main mechanism at work when electromagnetic radiation interacts with the atmosphere. In contrast to scattering, this phenomenon causes molecules in the atmosphere to absorb energy at various wavelengths. Ozone, carbon dioxide, and water vapor are the three main atmospheric constituents which absorb radiation. Not all gets through. Mie scattering, Rayleigh scattering, absorption, etc. The sun, if a perfect black body. The end of black body perfection. Black body radiation. 1 micron equals 1000 nanometers. Atmospheric windows. The windows are conceptual, not physical. Atmospheric windows. What happens when EMR strikes an object? Or is emitted by an object? Passive systems. Beyond vision. To remotely sense. The differences that make a difference. In remote sensing of the Earth, the sensor is recording the EMR reflected by the Earth's surface and by the atmosphere. Generally, we are primarily interested in the surface effects, and therefore understanding how EMR interacts with surface features is important. There will be object-specific wavelength-dependent absorption, scattering and emission of radiation. These effects provide the basis for identifying features in remotely sensed images. Images. Not the atmosphere. A surface's flatness is relative to the wavelength striking it. Examples of radar. The differences that make a difference. Bidirectional reflectance. EMR can be reflected like a mirror, specular reflection, reflected uniformly in all directions, diffuse reflection, or, as in most cases, the reflection properties will lie somewhere in between. SD. The angle at which the EMR strikes the object can have a significant effect, depending on the surface characteristics. Topography is, therefore, a significant factor. The differences that make a difference. Why vegetation is green. The differences that make a difference. Spectral reflectance curves. Vegetation under stress reflects that stress. Actually, it reflects less when under stress, and we can detect that. Spectral reflectance curves. The glue that holds it all together. Named spectral regions. It is useful to consider the different spectral regions, gamma rays, visible light, infrared, etc., and how important they might be to a remote sensor. Gamma and X-rays, almost fully blocked by the atmosphere, therefore of no use in satellite remote sensing. Ultraviolet, 1 to 400 nm, mostly blocked by the Earth's atmosphere, O3 absorption, but a window exists at 300 to 400 nm. Useful in detecting oil slicks. Named spectral regions. Visible, 400 to 700 nm, peak solar wavelengths, atmospheric window fairly transparent. The visible spectrum is typically divided into three regions. Blue, 0.450-0.495 Green, 0.495-0.570 Red, 0.620-0.750 Panchromatic. Read the CBC's handout. Named spectral regions. 0.50-0.90 How constant are these terms? Yellow and orange lie between green and red, but typically aren't named. Reflective near-infrared. 703,000 nm, 0.73.0 A number of atmospheric windows exist. Photographic IR is limited to 0.7-0.9 Thermal far infrared. 3.010,000 emitted by the Earth and other warm objects, majority absorbed by water vapor and CO2 in atmosphere. Named spectral regions. Thermal imaging sensors. Microwave. 0.1-3.0 centimeters. Wavelengths used in radar. Atmosphere window fairly transparent. A large number of named microwave regions. Spectral regions. At any given time, our ability to detect EMR is limited by the current technology. Therefore, every sensor reflects a compromise. A decision has to be made as to which regions to detect. That is, we can't detect all the useful EMR regions, so we detect those that we feel would provide the greatest amount of information. Every sensor is designed to detect selected bands within the various EMR regions. Thus, although spectral reflectance is a continuous curve, the use of bands discretizes that curve. Analog versus digital. Sensing a compromise. Sensor. Near. Infrared. Near. Infrared sensor. Blue. Green. Red. For example, ASTER, Advanced Spaceborne Thermal Emission and Reflection Radiometer, is an imaging instrument flying on Terra, a satellite launched in December 1999 as part of NASA's Earth Observing System (EOS). ASTER is being used to obtain detailed maps of land surface temperature, reflectance and elevation. Sensing a compromise. Note the increasing funnel sizes, aka decreasing spatial resolution, as the wavelengths increase. 15 meters visible in VNIR, 30 meters SWIR, 90 meters TIR for ASTER images. To each their own. EMR is the thing being sensed by remote sensing devices. EMR is affected by the atmosphere absorption, scattering, transmission. Atmospheric windows. EMR is affected by the target, absorption, reflectance, transmission, emission. This effect is dependent on the angle of incidence. All of these effects are wavelength dependent. A. Summary. Regions with the M spectrum are dissected into bands by different sensors. The shorter the wavelength, the easier it is to detect it because it has greater energy associated with it. Sensors can be either active radar, lidar, or passive, e.g., MSS, SPOT, ASTER, MODIS. Summary. GOTLAND island and phytoplankton swirls.